Yes, welcome to our talk on or on our masterclass on graph-powered machine learning from graph analytics to graph ML. So we'll talk today about different use cases, different techniques by which we can merge machine learning and graphs, which is a topic which is very dear to me because I really see the value proposition, also the uptake recently, but more about that in the coming slides. Probably most important piece of information of this entire talk is here's a bit.ly link either in the chat or also here on the slide, the front slide here, because that will give you access to the live slide deck. So there's, I suppose, a PDF version also available, but often if there are some questions during the talk, what I'll do, I'll go in and actually potentially even add some more slides or other things to this live slide deck. Furthermore, all the links to all the exercises are also accessible from the slide deck. So I would say this is something worth copying and maybe just open up that version in your browser. Okay, having that said, what will we cover today? So we'll start on a quick refresher on graphs, a quick refresher on different graph databases or ways to store and query graphs. But then we'll dive into the real interesting aspects, starting with graph analytics, and then going a bit more into the realm of really graph machine learning, where we talk about graph embeddings, where we then talk about graph neural networks. And of course, all of that is interlaced with use cases and also exercises or kind of Jupyter notebooks where we can try that hands-on. Challenges. This is originally, this used to be a 1-week PhD workshop I taught last year in Denmark. Of course, it has been upgraded and updated since then, but the basis actually was like a week-long course. And today we have 2 hours. So if you take a look at the live slide deck, what you'll also see, there are a lot of hidden slides, which might give you more information. But I think this is, let me actually just skip over to the next slide. What makes it even more important, this workshop, it's really for you. So I think given this short time frame, we should actually work together. So at any point in time, please feel free to share your expectations, any questions or also feedback, ask for breaks if needed. So I think then we can actually get the most value out of that for all of you participating. Then just briefly about myself, Jörg, I'm CTO at ArangoDB. It's a graph and beyond database, so I actually deal with those topics on a daily basis, which is something very exciting. I'm very happy that I have this privilege to do so. My career before I've mostly been focused on database systems and large-scale distributed systems, so I also kind of got in touch with some of the analytics topics throughout my career. But as mentioned, this workshop, it has a number of interactive Jupyter notebooks attached. There's a GitHub repo backing those up. You don't have to copy that, but if you have some ideas or if you want to make pull requests, feel free to go directly against this GitHub repo, or there are also more notebooks and we'll use throughout this class here. So feel free to check out what else is there. Feel free to share that with colleagues. This is all open source. Anyone can use or contribute here. But for this workshop itself, you don't need to remember this. It's all linked from the slides. With that, let's actually get started. Why should you care about graph analytics and graph machine learning? If we look around, I think there's been this trend towards graph databases or graphs, which most of us have been following at this conference for the past years. But I would say within that last 3 to 4 years, especially graph machine learning techniques have been really taking off in many different use cases. So for example, Google is using graph machine learning to improve the ETA predictions on Google Maps. Uber Eats is using graph machine learning to improve recommendations. If we look at computational chemistry, they have been using graph techniques for years. And also if we look at recent breakthroughs in research, also at like NeurIPS or some other kind of A-class machine learning conferences, we see a lot of growth in papers concerning graph or graph machine learning in general. What is kind of why is it taking off? So I believe right now we are in a place where we start to understand that there's information in the neighborhood or in the relations of different individual data items. So we'll also see that coming up on one of the slides. But the example I always give, imagine this here in the middle is a social network, and you're trying to predict churn of people from your network. If you look at traditional machine learning, you would take each individual user and then try to predict, based on certain features, what is the likelihood of that person churning? But if we actually know that all your friends, so all your direct connections have just left the network, this will make your probability to churn pretty high given two factors. First of all, your friends have all just left that network, so probably there's little value in you for that. But also, very likely you'll share some values or some reasons why your friends' direct connections have left as well. So also based on those factors, you're more likely to churn. And this is something we can capture in, it's called like traditional machine learning by creating features. So for example, we might create a feature, what percentage of your friends have just left that network, but it's something we would have to feature engineer and create explicitly, and also update explicitly, of course, as well. But if we just take a native approach to graph analytics and graph machine learning, we can really utilize the relationships and neighborhood information directly without having to create specific features for that. So let's get started with graphs. So if we look around, we are actually surrounded by graphs. So from social networks, from computational chemistry, from recommendation systems, event graphs, Internet of Things, or interconnected devices, or even if you just look at like 3D point clouds or even images, often come down to graph processing. For example, also natural language processing, if you dive deep, is heavily connected to graph processing. As already mentioned, also chemical molecules, they're basically graphs connecting atoms into molecules, so a graph. And here also graph techniques have been used for quite a while. So if we look at, just to get some of the different, same concepts here, same naming conventions out of the game. So I think graphs are data structures where connections are first-class citizens. And this is also often I get the question, when would I use a relational database? When would I use a graph database? It's really if we start to value connections as an important entity of information, and that it's not necessarily the connection itself, but can also be leveraging them in a graph traversal, for example. I would say then I would also recommend to go for a graph database instead of trying to force a graph schema into a relational database. A graph consists of vertices and edges, or nodes and connections in between. Then we have the concept of neighborhood, which is basically the directly connected nodes. So for example, here, the neighborhood of our node 0 is 1 and 2 because they are directly connected. Then furthermore, we have the notions of distance. So for example, how many steps do I need to take from getting from 0 to 4? That would be 2. Diameter, referring to how large is our entire graph, like how far is it spread out? Or in other terms, what is the longest, shortest path between any two vertices in that cluster? In that graph. And then we also have the notion of degree, so the number of connections for each of the vertices for each of the nodes. If we have a directed graph, so if we actually have here a little arrow, meaning 0 is connected to 2, then we can also further distinguish between an in and an out degree. Here, the example I typically give for an undirected versus a directed graph, if we stay in that realm of like social media, if we take a look at Facebook we have friends. And this is a reflexive relationship. So if I'm friends with someone on Facebook, that person is also friends of me on Facebook. If we, on the other hand, look at Twitter, there the notion is follower. And so I can follow a person, but that doesn't necessarily imply that that person is following me as well. And so in that realm, Facebook is an undirected graph because we don't have any direction of the edges, whereas Twitter has a direction, and the direction would be follows another person. Furthermore, we can have weighted graphs. So we can have a little weight here on the edges connecting different nodes. And for example, if you look at a map, there the weights are pretty natural. What is the distance in between 2 points on that map? Or if you look at a train network, what is the time to travel from one city to another? But there are many other examples for weights within graphs. Graphs can be sparse or dense. So this refers to like how well are they connected. So the most dense graph would be a graph where every node is connected with every other node. The most sparse graph would simply be a single node out in that graph. So it's typically, this is interesting to analyze because it will give you some insight into the connection structure of your graph, for example, and might also imply how you might want to store your graph, which we'll get to next. Another notion you'll often hear with graphs is the notion of cyclic or acyclic graphs. And so here, for example, we have a cycle. So we can basically go around and end up at the same node. And acyclic graphs, on the other hand, don't have any cycles within them. And if we now combine what we have learned, there's an important class of graphs, and that would be directed acyclic graphs. And that's, for example, if you have some scheduling, or if you, in database systems, if we look at transactions, and we try to represent the dependencies between transactions, dependency A is waiting for transaction B, for example, then what we want to achieve is directly acyclic graph, because if we have cycles in that graph, this means we would have a deadlock within our transaction system. So it's a pretty important class. Furthermore, and this is also the other factor, as mentioned, when to decide when to use a graph database or when to use another database, is to actually look at the queries we want to answer from this graph data set. So queries where it's really centering on the connections in between, for example, traversals. I want to find all the nodes in a tree-hop neighborhood which follow a certain criteria, for example. Or we want to search a particular node which has connections to a neighborhood node. So we want to search for a particular graph pattern across our entire graph. And those are simply queries where graph databases are really optimized for answering. Graph representations. So this comes down to the notion of how to store graphs. Interestingly, like graph representation is a slightly overloaded term. We'll see a different meaning later on during this talk. But here it's about how can we actually represent a graph. So how could we feed in a graph into a computer? Because like drawing it might work with some interface, but there needs to be some representation behind. And the most common representations we'll see on the next slides: adjacency matrix, incidence matrix, adjacency list, or graph Laplacian. But let's go through. So adjacency matrix is basically if n is the number of nodes, it's an n by n matrix, where we have a 1 if those two nodes are connected. So for example here, n1 is connected to n2, and n2 is connected to n1. In this representation, if we are dealing with undirected graphs, interestingly, or as you probably can see, it will be mirrored across this line here going through. And so if we have an undirected graph, we can actually save storage from the adjacency matrix by either usually just focusing on the upper right half of that matrix. Next, we can have an incidence matrix. And that incidence matrix is basically saying which of the nodes are incident to any of the edges. So for example, here, our node N1 is incident to the edges A and D. Similarly, N2 is incident to A, B, E, as we can see here as well. Next would be an adjacency list, and potentially I should probably change that away from a tabular format, but it's basically a list of the nodes adjacent to a particular node. So N1 is adjacent to nodes N2 and N4, whereas N2 is adjacent to N1, N3, N4. If we get later into a bit more advanced topics, such as a spectral graph machine learning, we also deal with slightly more advanced representations, such as, for example, the graph Laplacian, which is, in short, just the degree matrix minus the adjacency matrix. So the degree matrix is basically what degree do I have on the diagonal. So N1 has degree 2, so we have 2 edges. And 2 has 3, etc., etc. And if we subtract the adjacency matrix from it, we get the graph Laplacian. If we have time later, we'll see why that is a helpful property to have. In short, it kind of represents the flow of energy inside such graphs. So if you would imagine you had like potential, electrical potential on each of the nodes, the graph Laplacian represents how that energy would flow throughout the graph. Okay. With that, we can actually just jump into the first Jupyter notebook. How many of you have dealt with Jupyter notebooks in the past? Or how many of you have not seen a Jupyter notebook? Let's open that up. So in short, Jupyter Notebooks, I feel they're a really interesting way to combine executable code plus documentation. Here, we are using Colab. So this is infrastructure sponsored by Google for running those notebooks, but you can also run that in NB Viewer or any of your favorite systems out there. I just tend to choose Colab because it makes running it very easy for everyone without having to set anything up. In some corporate networks, people had challenges in the past to connect to it. If that's the case for you, just please reach out in the chat. So what we can do is simply here hit that little run button and then execute the code. So the first is just setting up our environment, but then here it actually gets interesting. So we can create our first graph, and then we can add our edges. So here we basically define a graph by the edge list, and then we can draw it. So here we started drawing it, and we can actually also show different different information or different properties of that graph. Furthermore, here we can also then create a directed graph. We can create a weighted graph, and this tool Network X, we'll see a bit more about it later on, also gives us like nice generators. So for example, here we can create a complete graph. Complete graph is the most dense graph there is because all the nodes are directly connected. And so here there are a lot of generators which make it very easy to generate certain graphs. I would now propose, you only have to go till here, but I would give you like 2 to 3 minutes to open up that notebook, see whether it works for you, and ask questions. Feel free to play around. For example, here we can add another edge. So which one is missing? I think 2 to 4 is missing, if I see that correctly. And just try to get a feel for what it means to execute code in a Jupyter notebook, and maybe also what it means in terms of creating graph and how that will impact those properties we see down here. And at any point, please feel free to ask questions in the chat. Traversals. Oh yeah, you're right. Thanks. I'll fix that right away in the GitHub repo in the background. Okay. So thanks for finding the typo. I already fixed it in the GitHub repo. Okay, with that, are there any other questions regarding Jupyter notebooks or creating first graphs out here? Then I believe we can continue. And trust me, we'll get more interesting notebooks as well. Graph databases, or yeah, how can I store my graphs? There are a bunch of graph databases out there, Neo4j, Neptune, TigerGraph. If you look through the lineup of this conference, you'll also see talks by, I think, all of those about those different databases. And I also don't really want to get into a debate which one is best, as I might be biased. But what I briefly want to touch up on is the different graph storage models. So I would say there are two types of graph storage models. So the one is a graph property model, and this is followed by basically all of the database systems on the previous slide. And then on the other hand, there's the RDF and triple store. So this is what we often see with knowledge graphs. This is, for example, if you look at Wikidata or other systems, and the name comes from that we represent all the information by triples of information, so subject, predicate, and object. What I'm seeing, I feel in the past, those two camps of people have been quite divided. Often it was people in industry or application developers favoring the property graph model because it makes it really easy to get started, whereas people really building large-scale knowledge graphs and trying to share data across different organizations, their triple stores have an advantage, as everything, as you can already see here, is indexed or referenced by often global URIs, unique resource identifiers. So luckily, there's those two camps are getting closer to each other. So for example, RDF star is a recent proposal which makes it much easier to combine the property graph and the RDF world. And so I'm kind of hopeful that this interoperability will become better between both worlds, because I believe both worlds have some unique benefits to bring to the table. Next, let's briefly touch upon machine learning. If you are not familiar with machine learning, if you look out for most of the tutorials out there, I feel they are really focused on deep neural networks at the moment, or deep learning. And we'll get into that also in a sec. What I always recommend is try to get a broadened understanding what else is out there in machine learning, because a lot of the other techniques, such as support vector machine, random forest, or other tools, can give you either better or also more interpretive results in many cases. why is machine learning taking off, or why are we turning this data scientist sitting at his laptop being able to use TensorFlow into the superhero who can do really cool tasks? There's, from my point of view, three main factors contributing here. First of all, we simply have the data sizes available. So we have enough data available to train a GPL 3 model, to train really large models. Of course, we need a lot of data for those. We have the compute resources available, and furthermore, we also have the, let's call it like techniques or research available, the model techniques such as convolutional networks or other things, which really allow us to leverage and scale the computation to those data sets across large clusters. As as mentioned, kind of the quick take on deep learning. I think deep learning is a great tool which is helping us in many cases. So there have been breakthroughs in image recognition, in natural language processing, in translations. So I think it's a really great tool. I just feel it gives for many people this promise that it's just going to do everything for you in terms of machine learning. So the kind of promise, how people often interpret it is, in traditional machine learning, the flow is kind of like I have some input data, then I'm doing feature extraction or feature generation, then I can run my algorithm and then getting some output. The hope is that deep learning will actually learn which features to use explicitly, which to some degree is true. But on the other hand, keep in mind, the more you do upfront to clean your data, to generate features, the higher quality your data is, the better the outcomes of deep learning will be as well. So I often feel this is a bit of an overrated promise. So just be aware of that. How does a process work, or in general also the machine learning process? It's divided into two steps. So on the one hand, we got the training, where we train a model that can be a deep neural network, or it can be something else. And once we have trained that, and it's often a really expensive process, we can then use our trained model to do inference, or basically to apply it to new data sets and get production value out of it. And this is a case where I can then actually use the model and get value out of it. If you never touched up on deep learning, deep neural networks, I just want to give, we're not going to go through, but just want to give a quick detour to the TensorFlow documentation. So TensorFlow is one of those, I would say, together with PyTorch, most frequently used toolkits for machine learning. And interestingly, their entire documentation, or almost the entire documentation, is also based on Jupyter notebooks. So they basically turned the documentation into executable notebooks, which I find quite useful and interesting because it makes it really easy to get started and just play with those things. Okay, back to the slides. And let's finally get into graph-powered machine learning. So basically combining graphs and machine learning. And what can we do with that? We can identify information about important or influential entities within our graph. So again, in a social network, that might be the question, who are the influential person, or who are the important persons within that graph? In a routing telecommunication networks, it might be where the single failure or the like dangerous failure points within that network, or similar aspects. In later slides, I think in 4 or 5 slides, we'll see that the notion of what is important can have very different meanings depending on the graph we're talking about. We can also use it for scheduling or event connections, taking a look at supply chain networks. If you look through in the last years, Corona and other situations, it really made this entire global supply chain management a lot harder. And there's more and more need for trying to predict either weaknesses within one supply chain or also just impact analysis. If a ship gets stuck in a Panama Canal or a Suez Canal somewhere, what is the impact on my supply chain? How can I circumvent that? So again, if you think about a supply chain, this is also in the end a graph, and so we can apply graph-powered machine learning, graph analytics to analyze our supply chain. The question, are two graphs the same? So graph isomorphism seems like to us a pretty simple question, but it's a very crucial question looking at computational chemistry. So if you're trying to predict, are those two molecules either the same or are they similar, it might not be as easy as in this example, because those can be pretty large graphs. And so here we are nowadays often also deploying approximate techniques to judge whether two large graphs are the same or not. Furthermore, anomaly detection or fraud detection, where something in my login structure, in my user network, in my telecommunication networks, where is something unusual, either is someone trying to break in or is something broken right now. We can also leverage graph-powered machine learning to infer knowledge, or maybe the last example, to identify certain subcommunities. So if we have a large graph, usually there are some subcommunities within that graph, and we want to identify, who's belonging to which of those subcommunities, or where those subcommunities located. The next question I usually get asked is, how does graph machine learning differ from traditional machine learning? And I gave in the beginning this example of trying to predict churn within our social network. And if we would formalize that a bit, it's that default machine learning would take the assumption that each of the persons, each of the users are independently and then typically also identically distributed data. So this is one of the at least common assumptions for machine learning models, IID. And if we look at real world data sets, this is often not true. So we had that example of our social network where if all my friends leave, I'm also likely to leave. And that actually comes down to a property called homophily, that neighboring nodes are similar or have similar labels. Other invariants or other properties of real-world data sets are that we often have structural equivalent nodes. So if we, for example, look at routing networks, or again, let's look at a social network, we have certain influencers which kind of form, if we look here, like there are certain structural nodes which kind of form the center of a certain subcommunity here. So they are highly connected nodes. And often those structural equivalent nodes, they will share certain properties and might have different properties, for example, from the neighboring nodes here. Then there's also the opposite of the first assumption of homophily, that neighboring nodes are actually different. And that might be the case in, easy example are just bipartite graphs where I have two distinct items. So I have users and then products which might be bought by them. Then obviously neighboring nodes are different, but even in more homogeneous graphs, often there are scenarios where neighboring nodes share different properties. So how does it fit into this picture of graph databases? So I kind of feel it's a continuum with different steps out there. So on the one hand, we have simple graph queries, like identifying an explicit pattern, finding a common connection between two nodes in a graph. I would usually describe those as graph queries, and this is what any graph database should be good at. We basically query about that connection we mentioned in the beginning. Next, then there's graph algorithms and graph analytics. And this is when we look at certain additional properties. So for example, shortest paths between two nodes. Here, we cannot just look at the connections, but we have to look through all different connections in the graph between two nodes, which might be possible, and then keep in mind and filter out which is the shortest one. So there's a quick jump over to graph analytics, and this refers to getting overall insights from a graph. So I would say, like, on the one hand, graph queries, they're often also like very local to a graph, whereas graph analytics, we try to extract some value from the overall graph. So for example, where are the important nodes in my graph? Where are certain subcommunities in my graph? Next level is then really graph machine learning. And here I would distinguish between, I would refer to graph machine learning as typically when we touch up on some statistical models. So graph analytics is really an analytical model. If I rerun that, I'll get the same results. But if I'm taking a look at graph machine learning, I often work with a statistic, or usually work with a statistical model. Can be a deep neural network, can be some other kind of model. And then I leverage that to generalize or again solve an unsupervised or supervised machine learning task. What does it actually mean in a concrete example? So the Cora citation network is a common data set used in graph research and also for benchmarking graph systems. And basically it's a connection of papers, like which paper is citing what other papers. In addition, we have some additional labels, some additional content. So if we had a simple graph query, this would be who cited a certain paper. So just give me all the other papers who cited it. Pretty simple query. Then if we take a look at what graph algorithms or graph analytics can do for us, it would be the question, which is the most cited papers, or where are sub-communities which are referencing each other? So either fields, or in real science, it unfortunately also happens that certain research groups are citing each other over and over. So you can try to identify those sub-communities or cycles in the graph. Then if we look at GraphML, we could solve tasks such as trying to predict reviewers, trying to predict missing citations, trying to predict feature labels or other things we've seen. And this then comes in, we try to generalize that knowledge we've seen and try to apply it to previously unseen papers, for example. The hard part now comes that often we even have different options available. So the tool set in graph machine learning is rather large. So for example, just that task of trying to predict paper labels. So here we have certain labels, what a paper is about, and what are different techniques we can choose here to solve that. We can use label propagation. So label propagation, each paper is basically sending its labels to its neighborhood, and we do that over and over again. And then we, for example, just pick the most frequently seen labels for unseen ones. We might use a graph convolutional network for this, or we just might get a graph embedding and deploy more traditional machine learning techniques such as support vector machine or other things for classification. If embeddings or graph convolutional network doesn't ring a bell right now, don't worry. We'll get into those details when we touch up on machine learning. But I think the core method should be, often you have different tools available and different choices available. This is what a talk of mine tomorrow will actually touch up on, graph analytics and graph ML. So where's the trade-off between different techniques? Where's the trade-off between different tools? Just as a teaser, kind of the questions you would ask yourself when trying to choose between graph analytics or graph machine learning is, for example, is a simple model sufficient? So if it's sufficient that I deploy a very simple graph analytics algorithm and that scales to my data set, great. The simpler the model, the better. Of course, also the less data I'll need, the more interpolative it will be. So simpler usually in machine learning is a better choice. Next question would be, is there a need for an exact answer? As mentioned, graph machine learning relies on statistical models. So if we really need an exact reproducible answer, probably we either have to see the trade-off, how exact that answer has to be, or we have to resort to more analytical techniques. Next point would be, how big is the data set? How dynamic is the data set? So graph analytics as we need to touch upon the entire graph, can become really expensive when dealing with large data sets out there. Whereas on the other hand, taking a statistical model, we can work with a smaller neighborhood. So depending on how complex the model is, if we again have a simple model, the graph machine learning will scale to larger data sets. Second part is how dynamic is our data set. So how often does it change? So imagine, for example, a lot of people Facebook, LinkedIn graph of users. This, of course, is changing every minute. There are people joining, there are people leaving. Was there a question? No. Okay. And so that graph keeps updating over time. And so here, this is also referring to question number 5. The question is whether we need something like inductive learning. So graph analytics, typically, if something changes, I have to start, most of the time I have to start over again. Whereas I have modern graph machine learning statistical models, they can actually serve for inductive learning. So also apply to previously unseen or changed data sets. Next question is then, where are the performance requirements? If we take a look at graph machine learning, this will actually be split in 2 phases. We have a training phase for training our model and then the inference phase. So in many scenarios where we can actually split those into 2 parts, an offline training part and then an online inference part, we can get pretty quick results from graph machine learning models. Last but not least is the point of, do we need explainable results? So do we need to understand, for example, in healthcare or finance, how did we arrive at a certain conclusion? Then there, of course, graph analytics is a clear advantage because, yeah, it's analytic and we can really dig deep and more or less easily understand how a certain decision has been made. Graph machine learning or machine learning in general, there's a trend towards more explainable models, but I would say that's an area of active research. Okay, with that, unless there are any questions, I would dive into the area of graph analytics a bit more. 3, 2, 1. Okay. Graph algorithms. So how can we extract knowledge from a graph? So on the one hand, we got search and traversal algorithms. So for example, we try to find a particular node or we try to find a particular edge. For example, if we have a heterogeneous graph with different node types, we're trying to find an edge connecting an movie node of type movie with a node of type director because we are interested in the movie director pair. That could be a search or traversal problem we are trying to find. Next class of algorithms is concerned with path finding. So how can I get from A to B? And there might be different classes of that. What is the shortest path? What is a redundant path? You also might want to get all the different paths to get from A to B. So there exists like a number of variants of this how do I get from A to B problem. Next, and I personally find very interesting area of such graph algorithms is the notion of centrality. We touched about that a bit early in the introduction. We want to say we want to identify important nodes in that graph. And the bit more technical notion is we want to identify central nodes in a graph. And depending on what that means, what central, what important means for us, we might have different measures we'll see in a second. Cycle detection, we also briefly touched upon that already in a database system or somewhere where I try to identify cycles between different transactions depending on each other for deadlock detection, also more general network analysis. We might be curious about whether there are cycles within our network or whether, for example, we really have a DAG, a directed acyclic graph available. Then we also have community detection, where we try to identify separate communities within that larger subgraph. So do we have any concrete subgraphs out there? So problems we can deal with graph algorithms. So for example, minimal spanning tree is one of them. If you dealt with programming challenges for interviews or somewhere, you might have come across that. The question is, what is kind of the subgraph, the DAG, the uh, subgraph without any cycles that is minimal, so where I have the minimal cost. And this has a large number of interesting uses. So of course, for example, for a network protocols, I think border gateway protocol depends on it, but also many others. Also for image segmentation, this can be used. Here's a link to the Wikipedia article for that. And also in general, where I might just want to consider a subgraph of the entire graph, also minimal spanning tree might be a way of identifying the subgraph. Shortest path, I mean, kind of obvious. What is the quickest way from getting from A to B? Still, there exist a number of algorithms for doing so with different properties. For example, considering negative edge weights or other things. Then there are also different variants. So for example, I might be interested in the k shortest path. So not just the one single shortest path, but the n or k number of shortest paths. So I have a backup if, for example, something fails. Single source shortest path, I might want to identify from node 1 the shortest path to all other algorithms, or even the all pair shortest path. So I want to see the shortest path between all pairs of nodes. And here, obviously, improved algorithms exist and computing n times or n times n minus 1, the shortest path between all nodes individually. 1 second, yeah. Community detection. So we try to identify certain subcomponents. So often connected, weakly or strongly connected components. We might, again, also deploy label propagation for that. So if nodes have certain labels, we might propagate them and try to find what's going on or where we accumulate the same labels in the end. And interestingly, I think this is already one of those scenarios where we see two different kinds of graph algorithms or two different kinds of information we are using. So here on the upper side, like we only use structural information, how are nodes connected. But if we dive into that area of label propagation, we might use actual labels of the nodes. So it might be, again, for example, churn probabilities or some other labels which we already have on those graph nodes. And this we'll see later on as well with those graph-powered machine learning or different machine learning models. How much of information can they leverage? Do they only rely on structural information, or do they actually distinguish between also property information or even edge information out there? Then last, and as I've promised earlier, centrality and the different meanings of centrality. I think if we want to identify in the graph here on the right, what might be the most central, most important node, an obvious measure is the most connected node. And this is also referred to as degree centrality, and that would be this blue node here in the middle, because it's just connected to most other nodes out there. The next measure is the closeness centrality. Imagine, for example, we're trying to figure out where to build a certain distribution hub or something like that. Then we are not just interested in like the direct connections to most nodes, but we probably might be interested into like the average closeness to all nodes. We want to be able to reach all nodes on like average, an optimized average cost. And this is what the closeness centrality. And here, if you count what is the distance from all those green nodes to all other nodes, you'll see that they all have the same average cost of getting there. Next is the betweenness centrality, and that refers to how important a certain node is in connecting other components, other subgraphs out here. And so this is, for example, if you're analyzing routing networks or other networks, This is a metric where, hey, if this node fails, you can already see this will deteriorate into two subgraphs, whereas if this node would fail, we can still reach all nodes from all other nodes. So what is kind of like the failure impact of a certain node, if you want to view it as such? And the notion of that is how often a node appears on the shortest path. So if we compute all the pair shortest paths, so shortest between all nodes, the question is how often does a node appear on the shortest path? Okay, next comes to a particular algorithm or so-called transitive influence, and that's PageRank. But before, let's actually maybe briefly go through PageRank and then go over to the exercise. So PageRank, I think for me, PageRank is this example where Google has turned or has interpreted a particular problem as a graph problem. And that made Google very successful in the beginning. By now, they're not using PageRank anymore, but in the beginning, it was used to kind of rank the results. Which website should they show you first if you're looking for graphs on the internet or for connected data world? Which results should they show first? And the approach PageRank takes to that is so-called transitive influence. So basically, the number of links and the quality of links determines how important I am. So if I'm a website which receives a lot of incoming links from other websites, so for example, let's take here the yellow bubble here on the right. It gets a lot of links from those green ones down here, from the blue one and others. So the more transitive influence I'll get. On the other hand, I can also be important or central if I'm getting references from only few but very important sites. So imagine, for example, Wikipedia is referencing you. So here, yellow is Wikipedia, and we are that red side being referenced as the source of truth, the main reference for graphs. Then probably we are also pretty important. And this is what's considered as transitive influences. You can imagine the importance kind of flowing through that graph here until it becomes a stable graph. And the other way in which you can interpret that problem is how likely is a random server ending up at our page. So a random server, he'll start on any of the pages, he'll have n number of clicks, and how likely will he end up on one of those nodes. And then you can already see if we are coming from like those small nodes which don't have any incoming ones, it's very unlikely that someone will end up there. But on the other end here, as a lot of links are coming in, so it's likely that someone will end up here. And similar, as someone is likely to end up here, as there's only like one link going from here, there are also people very likely to end up here on the C node, because yeah, just a lot of people are likely to end up on the B node here. And we'll dive into how they can be computed in a second. With that, I would actually lead you over to the next part of the exercise. And if you still have it open, it's the same notebook as before, but you can also use this link here. And now we are concerned with the second part. So here under Graph Algorithms, if you still have the first version loaded, just get rid of the NX here. If you reload it, it should hopefully be gone. And then we can go in, draw our graphs, do things like depth first, breadth first search across it, find shortest paths with different algorithms. So for example, you can try to play with your graph and different algorithms, check out what happens if it has negative weights. We can do the minimal spanning tree, we can do cycle detection, we can have different centrality algorithms. And I think this is where I just want to give a short shout out to this Network X tool. I would always describe it as kind of the Swiss Army knife of network analysis or graph analysis in Python. So if your graph is small enough to fit on a single node, on a small single node, then this is a really great tool because it comes with a lot of different notions. And so just if you browse through here, the different centrality measures, you'll see how many options you have here. So I would give you again like 2 to 3 minutes to go through, and feel free to ask questions again in the meantime about algorithms, about graph algorithms, or any graph topic you're curious about. I suppose no one is having problems with Colab so far. Otherwise, if maybe just as a quick side note, if you're interested to do something like that, NB Viewer, there are other tools. I think I've linked them on one of the slides available where you can build that same infrastructure internally. So if you're interested in running tools like that, there's a lot of infrastructure out there that you can also host it internally, and you don't have to leverage some Google infrastructure for it. I would give 1 more minute and then continue. Okay, imagine now, yeah, again, we are Google and we want to run this PageRank over the, yeah, pretty much entire internet because we need to analyze the link structure. Obviously, a single machine will be way too small for that. So Google actually had to come up with a way how to process that across large large clusters of compute nodes. And here they developed a system called Pregel, which is still used in some derivations, also in other open source systems. So, for example, Apache Giraffe is also relying on the same model underneath, which is called bulk synchronous processing. And so the idea they had is they split the graph processing in two disjoint steps. So there's like a working step, and then there is a communication step, and those two form a so-called super step here. And at the end of each super step, we can have a barrier where we want to synchronize all the different nodes, or there are also other implementations available which simply go on. So we can basically imagine that system in like each of the nodes is processing its information, and then at the end, it's sending an update to all its neighboring nodes. So if you look here, we would, like each of the node would process all the incoming messages. Once it's done computing its new average here, so if you want to go, you can also go through this formula here on the right. We send an update to all our neighbors across a link, basically saying, hey, this is a new value, this is a new centrality value I computed from myself. And this continues until we reach, until not too much changes anymore. So basically, until the graph becomes stable. And this is This allows for a pretty large class of algorithms to be implemented in, not all of them. So for example, shortest path is just, you could implement it in Pregel, but would be a pretty bad choice. But on the other hand, like all pair shortest paths or something like that, is again a better fit to be implemented in Pregel. So how does it work in a concrete example? Let's try to find the maximum number in our graph here. At the beginning, all our nodes are active, and so what we do is sending our own value to all our neighboring nodes. So here, 6 is sending 6 over here. Here, 3 is sending 3 here, and so on and so on. Next, what each node is doing, it's looking at its inbox. So what messages it has received, and will compute the maximum value of its own value plus the number of incoming messages that it's seen. If that is higher, we update, and in that case, we also stay active. So for example, 6, it has received 3 and 2, but as it already has the largest value in that graph, it won't update it. And in that case, it will actually become halted, because what would happen if it would send its update again? This would be unnecessary information in the cluster because we already sent 6 in the step before. So we can stay calm and don't have to do anything. But for example, here, this node here on the upper left, we actually have updated our value to 6 because we received 6 as a message. So we would again send out a message to our neighboring nodes. And so this continues until basically every node is halted in that graph, or often most real-world life Pregel algorithms, they also will have a maximum number of steps in case the graph doesn't converge after all. We have an optional lab to Pregel. I would probably skip it just due to the amount of time we have left. But if you're curious, you can just jump into that later. What I would like to go in instead is different use cases, or it's called like how to spot a graph problem out there. And I suppose most of us have seen either this ad on Amazon or this box on Amazon or something similar on other nodes. So basically, customer who bought a particular item also bought something else. Or if you're Uber Eats, you're trying to recommend new dishes, you might recommend dishes who someone else has ordered who also ordered similar dishes as you. So this process is called collaborative filtering. So you try to use that collaborative knowledge in trying to filter new products for a particular person. And yeah, given those times we live in right now, I think a question to ask could be like, what films could we watch if in case we have to isolate? So fortunately there's a cool data set available from IMDb, movie ratings, and this is pretty much a bipartite graph. Bipartite graph means we have two distinct set of nodes. So we have user nodes, and they're rating movies. So we also got movie nodes, and then there are edges going in between, which pretty much means like user rated a particular movie. How can we turn that into helping us to find out movies I will like? And again, this is the collaborative filtering. And if we had to put it in words, it would read something like this. We want to find highly rated movies by people who also like movies I rated highly. So how can we translate that into a graph problem? So first, here we're starting with our little user here. We want to find movies which we like. So we need to kind of identify movies I rated highly. So we go over here, we filter on which movies I rated very highly, and really cool, we find a set of movies. Next, we actually want to traverse it back to the user side of the bipartite graph, because we want to be able to identify users who are similar to us. So we want to find users who also rated either the entire set or some of those movies as highly as we did. So we basically go back in this graph and identify users who are similar to us. Next, then we will again step over here, but now try to identify additional movies which have been also rated by those users whom we identified to be similar to us, which they also rated very highly. So basically, we turn that into a graph pattern or graph traversal where we go back and forth in this graph until we identify an additional set of movies which similar people like as well. And so this would be an example on how to interpret, again, a problem such as recommendation as a graph problem. We'll later see also how Uber Eats is kind of taking that to the next level by deploying graph machine learning for a similar recommendation task. So if we want, I'll just give you a brief walkthrough what's happening because it's the first notebook using a cloud instance in the background. It's pretty much the same, and you pretty much are running through this example in a property graph database. And so kind of the special thing happening here is we get from the ArangoDB cloud service, we get a temporary database. So this will live for 4 hours. Once this is there, we can leverage that for the next 4 hours. So we could, for example, also log in. And I just wanted to show that that you're aware of where this database is coming from and that you're aware that this is temporary. So if you're playing with that, you can hit it with any queries, but just be aware it's temporary. And then if you want, we can either take a few minutes right now. Yeah, let's actually walk through. It should be quick. If that would display. Yeah, here. Yeah. So here is our input data. So often, even for graphs, we often get our input data in CSV files. So here, the IMDb data comes in 3 different types. So there's a user data, there's a movie data, and then there's a rating data. So kind of looking as follows. So here in user data, we have some description of each user. Movie data, we have some description of each movie. And then we have the rating information linking the user ID to item ID with some kind of rating. And this is a format or a related format by which we often get our graph data. And often this is one of the most challenging steps in actually turning your data into a graph. And so here we do that by first creating our collections. So we create a user, movie, and then a rating collection for the edges in between. And I would often recommend, if it's not a total trivial problem, just write a small piece of code for actually generating that graph. ArangoDB, Neo4j, Tiger Graphs, they all have tools for importing it. If you're using those, it will actually write this logic for you in the background, how to map things into a graph structure. Just keep in mind it should be reproducible. So you might want to store that and run that on a nightly basis for importing new data sets. And the rest is actually trivial. So we do the exact same steps we mentioned before. So first of all, we try to find our own ratings, which movies I rated here was rating 5, Groundhog Day, Horseman on the Roof, etc. Then we try to find alike users, so users who are similar to us, and then we want to find movies which those people also like. Let's see, is there anything? Yeah, Raiders of the Lost Ark is something interesting. So yeah, it more or less works, and we'll see more elaborate tools coming up. So I could give you now a few minutes to run through, but I would say as I step through, unless you want some time right now, then please write in the chat. I would continue in the presentation as we have 50 minutes left. You can always run all the exercises after class as well. So Network X, we've already seen that in the first notebooks. It's kind of that graph toolbox or Swiss Army knife for graph processing out there. What's really cool about it, it has a lot of connectors for loading and storing graphs in various formats. So if you're working with any kind of graph infrastructure, most likely there will be a network X adapter to load or store your data to it. Same, for example, holds for ArangoDB. Also, Neo4j has a network X integration, and I think most others as well. It's really great if you want to get a first look at your network and first want to analyze that. So often it's just kind of like this exploratory step of playing with a small graph. It's not meant for really large scale distributed processing. So as soon as your graph gets too large, probably it's not the right tool. But if you have a small sample from your graph, it's a very useful tool. Other tools, some of which are basically network X for scale, for example, NetworkKit, GraphTool, or Snap, they help you to scale out to larger data sets as well. There's an interesting blog post comparing some of those packages if you're interested in using that at more scale. Okay, with that, we kind of can leave the realm of graph analytics and go more into the direction of graph machine learning, starting with graph embedding or graph representation learning. It would be nice if the slide is showing up. I actually skip over that empty slide. And that leads to the question, what are embeddings, or what are embeddings used for? In short, embeddings are a way to embed or transform something unstructured into a structured space. So typically it means I want to take, in the case of graph and then turn it into Euclidean representation. Why do I want to do that? Simply because it can be useful by itself because I can easily compare vectors, like cosine similarity, cosine distance in between. But on the other hand, machine learning tools, they cannot deal with unstructured data. So machine learning tools, they need some kind of number representation they can actually deal with. And here we'll see how embeddings can basically help us in turning typically a node into some vector representation. The most obvious approach would just be to take a node and turn it into a random vector. But we would lose a lot of information through that. To understand that, let's briefly go over to that realm of word embeddings. So a lot of the embedding techniques, they originally come from natural language processing, where we want to map words to vectors of real numbers. And if we do that, we want to keep certain similarities in mind between words. So if we would just do that on a random level, it would end up somewhere in this three-dimensional vector space here. But if we look at certain characteristics or correlations of data, combinations of data, so for example, Spain, Madrid, Italy, Rome, they have a similar connection in between. So we would actually expect that the vector in between, if we would connect them in this three-dimensional embedding, would somehow look similar. Or also that they are not like at two opposite ends of our embedding, for example. So we want to keep some kind of context information around when creating those embeddings. Same holds true for graph embeddings. So here, most also in the right now, when we talk about graph embeddings, we most often mean actually vertex embeddings. So we take each node within our graph and turn that into a vector of numbers. And this is, for example, what node2vec, which we'll study in a second, is doing. But of course, there are also other embedding algorithms for edge embeddings or entire graph embeddings. So I can also have something which creates embeddings for all my edges or even entire graphs, as mentioned earlier, when we want to compare whether two graphs are the same. When doing so, again, we want to have certain context information preserved. So for example, the homophily we saw earlier, that interconnected nodes should be also embedded close to each other. So it would be kind of weird if those two nodes would end up like totally somewhere else on different spaces in our embedding, or also structural equivalent nodes. So here, the U and S6 nodes, they serve some similar purpose in each of those subgraphs. So we would also expect the embeddings to represent it and somehow be similar. As a short detour, another data set. So we already learned about the Cora data set, the citation network earlier. The other very famous data set in graph machine learning, graph analytics is the Sakari's Karate Club. So it's actually is based on some observations by psychologists, I believe, who observed interactions of people inside a karate club and also outside of class. So here the graph on the right is a social graph depicting whether some of those members interacted outside of class. So for example, here this edge means that 18 interacted with 2 outside of class. Maybe they went for a beer, maybe they met up for a run, something like that. What now happened at this karate club, it actually split into 2 subclubs. So here the instructor and the administrator, they each formed their own club. And the common task in graph analytics or graph machine learning is now to try to predict like where each of those other people, as they want to continue doing karate, in which of those clubs do they end up? And this is where we can already see the value of embeddings. We'll generate that ourselves in just a second. But in short, here, those are node embeddings for each of the nodes. And we took the color where they actually ended up. So red, I think, is then where they ended up in the one club, and blue are the nodes which all ended up in another club, just to depict where everyone ended up. And so we just generated that embedding here, and we can already see just on this 2-dimensional representation, typically we would choose a higher dimensional embedding, we can already distinguish and easily create a linear classifier in between those 2 classes. So let's actually see what's going on in the background. Yeah, let's start there. I was considering whether I wanted to show you the notebook first and then switch back. But let's actually continue here. So again, let's take a short detour back to word2vec. As said, like a lot of these embedding techniques are were originally developed for word embeddings, because here we face the same problem. We have some unstructured data, words, which we want to represent to some machine learning framework in a vector format. And so another way of creating it's very simple embedding, or a simple, very simple vector representation, is the so-called one-hot encoding. So we have a vector the size of our dictionary. So here we have 5 words. So our dictionary is of size 5. And then for the first word, we switch the first bit on, the second word, second, and so on and so on. So this is also called one-hot encoding. And now, what can we do? We want to use and identify, create training samples based on which words are close to each other. So which words are appearing in the same context. This is one of the reasons why we have those huge language models right now. And again, this is one of the reasons why machine learning is taking off right now, because we have machine-ready access to large data sets. So the rationale behind this is if we have words appearing in the same context, so for example, king and queen, they will often appear in the same context, for example, referencing palace, crown, prince. So those words are much more likely to appear in the context or in the surrounding of king or queen than in others. Then what we do with that, so in words, in text, natural language processing, we basically have those sentences, and we create training examples. So we try to create examples where we try to predict the context from a particular word. So here, for example, from Z, we want to predict quick and brown. So we create two training samples. Quick, we want to predict Z, brown, fox, 3 training samples, brown, quick, Z, fox, jumps. And then fox, brown, quick, jumps over. So we basically create those training samples, and now we train a dummy network with that. This is also called skipgram network. And it's a very simple neural network just having one layer. The interesting or the kind of fascinating part about this, and this is also why it's called dummy task, we are not really interested in this network for by itself, but we are interested for it for kind of this hidden layer. But let's first see how we train it. So input layer is our one hot encoding. So this might, for example, be the word king, and in the output layer it might be the word palace. And so we are trying to predict and optimize our network for predicting, having a high probability to predicting palace for the input word king. And if you're a little bit familiar with neural networks, you know this in the end, again, it's just a matrix representation. So in here, our hidden layer is in the end a matrix, and the dimensions of this matrix depends on how many different neurons we want to choose here. So if we choose 300, it would be a 10,000 words. So because our dictionary is of size 10,000, and then 300 neurons as input layers, as a hidden layer size. So interestingly, once we have trained that, we can interpret that also as a word lookup vector. So here, this dimension is 10,000. And so for each of those entries, this actually represents to the one hot and to the one word. So for example, king is the third entry. So king would be basically this row. And this is now kind of the magic here that we don't care about the network for its network classification performance, but we take that hidden layer and interpret it as a lookup vector. So again, this would be the embedding we want to look up for king, for example. And then with those embeddings, we can calculate the probabilities of things occurring close to each other. And basically, we end up with our embeddings. Great. We know how to do that from words. Now, how can we do the same for graphs? So words have or text has the advantage that we have a linear structure, or also called sentences. So we can basically go through and we can sample the context around it. So here we know, oh, those two words are close by. If we do the same within a graph, this is a bit harder because we might not all nodes have the same number of neighbors, so it's kind of very hard to create representative sampling as we would do simply by going through text. But we can sample nodes or runs from a graph. So basically we can go in, and the most simple thing we can do, we say we want to create sentences of length 5 from our graph. So we just randomly go from starting node to this node, randomly go here, randomly go here, randomly go here, until we have a sequence of 5 nodes. We can also do that a bit more intelligently by going in and having certain transition probabilities. So for example, we have 3 different cases in a graph how we could transition. So the first thing, we just transitioned over from T to V. So now we're here at this middle node and we are trying to decide where we want to go. The first option would be to go back to the same node we came from. So this is this first probability, 1 over P, and that would be the probability of going back to the same node. Second option we are having is going here to X1. X1 is also connected to T, so we would stay within the same subgraph, within the same triangle. Last option we have is basically none of those, but explore that graph further. So this is here either going to X2 or X3. And this is what's called node to vec. They basically allow you to play with those probabilities and hence control how you want to explore that graph. Do you really want to stay close by, or do you want to have large runs over large parts of that graph? So how does this then look like? So we have a random sampling. We first create our sentences from our graph. So here I created 4 sentences, and then we can deploy the same structure we had for word to vec. We create training examples, we train our skipgram network, and then we have our node embeddings available here. Having that said, let's actually do that in practice. So next notebook. And we need a number of libraries to load. This always takes a while. A quick question in the meantime. Do you think you all understand the value of embeddings? Why do we want to generate them? So we want to mostly generate them, A, because they allow us to have a vector representation, which we then can use in support vector machine or other things. Secondly, we'll also see that just also comparing vectors by itself can be already very helpful, just for like our visual representation. So let's get started. And feel free to, we'll give you some time to do that as well in just a minute. Here's, by the way, another typo. I'll get rid of it here, and I'll remove it as well. So Network X has a nice generator for the Karate Club example. It doesn't look as nice as the round figure we saw before, but still, it's the same graph in the end. Doesn't matter how we represent it. What we furthermore have is we have some information where they ended up in the end. So this is here that node feature, and it's basically saying club Mr. High, club officer. So those are the two competing clubs they might end up in the end. What we next do is we generate our random walks and then fit our skipgram model. One interesting aspect of those random walks and those sentences and node2vec in general, you see it doesn't take into account any of those features here at all. Again, recall what we talked about in the beginning. It only considers the structural information, which node is connected to which other node. But okay, we have that done, and now we can create the embeddings and actually display the embeddings. We can see here we have an X and Y coordinate, and we still have the same information as before about the club. So this was not related to the embedding. We just get it from the original nodes as additional information, and then just put it in here to display it. And then we can actually display it. This is not the nicest one. Let's rerun that. I like statistical models because we can rerun them. So maybe have 60 iterations. And show that again. Yes, this is a much nicer one. So we can already see here, if we now would train a linear classifier or any kind of classifier, we could easily separate those two classes between the Mr. High or the officer, people who joined the officer club in the end, and can also try to predict that for nodes where we don't know it. So I would give you 2 to 3 minutes to run through. So I think what's interesting is to actually play a little bit with those components. So the epochs, this is how many steps we want to generate. Walk length is how long should each sentence be. Number of components is how many dimensions should our embedding have. I would leave it for 2 to now because it's just much easier to visualize, obviously. And then you can play with those parameters, but I would not dare right now. But I think those are the interesting ones in real world scenarios I would first start playing with. And then this is just kind of like an outlook. There's a second example here about FIFA, so soccer club, where we can also leverage that to predict similarities between different soccer players, between different teams. This is a bit longer, but I think it's a very interesting thing to run if you're interested in graph embeddings and have some time afterwards, because it also captures, you'll see like half of this code is actually preparing the data sets, creating the graphs for each team, etc. And then here first we come to the node to vec algorithm, but that corresponds to my experience with dealing with real world data sets, because most often I'm spending most time preparing the data than just running it. So just try to go up to here, play a little bit with node to vec, and we'll continue in, yeah, again, like 2 to 3 minutes. You can also just ping in the chat once you're done. And again, as usual, feel free to ask questions in the meantime. Roughly one more minute. But you can already see this is a more statistical model in the end, right? Because if you rerun the random block generation or fitting of the model, because yeah, there's a random component involved, it will give you different results each time you run it. A question which I often get asked is, what do those different dimensions refer to? So X and Y. They don't mean, they don't necessarily have an explicit meaning. If you're familiar, for example, with principal component analysis, you can imagine it being some kind of dimension which is good at separating those two data sets. So it doesn't have a particular meaning by itself. So it just refers to the vector length in the end. Like how much information do you want to give to your vector? I mean, this is maybe this is good to quickly jump back here to talk about dimensions. The other reason why we obviously want to do that, if we take a look at this very simple embedding where we either use the one hot encoding or assign a random vector for each of them, we don't have like control, or in the case of one hot encoding, our vector needs to be as large as our dictionary, which you can already see for large dictionaries or even changing dictionaries won't really work. So the word to vec or those embedding techniques, they give us a way to control how much resources, how much money do we want to spend on that representation. So if I can choose the hidden layer here, the number of neurons, or if we go over to the notebook, I can choose a number of dimensions here, components. I can control how large my representation should be, so, or how complex it should be. Okay, then with that, let's briefly talk about what is bad about node to vec. Do you have any proposals why you would say node to vec might not be the best tool out there to use? Let me maybe ask the first question. What happens if that graph, I don't want to cross, Josh, no context. So if I interpret that, I think you mean we don't take any of the additional information on the nodes into account. It's really just structural, if I would interpret that. Yes, This is one of the big draw sides of Node2Vec. The other one, we talked about inductive techniques before. So what happens with Node2Vec and this embedding if my graph changes, or if I'm adding another node here? What would I have to do? So I'm adding here a node G, which is connected to X3 and X4. I would have to go in and actually rerun this entire procedure. So this is what's typically called transductive method. And this, as you can imagine, if you have dynamic large graphs, this probably won't really scale to your data side. Yes, Stefan, you're also completely right. Attributes of nodes and edges. True, edge metadata is also something crucial to consider, and we'll get to that in just a second. So, for example, I always would say, like, imagine those are different node weights. Like, this is a really strong connection. Imagine this represents, I don't know, interactions of people have with each other, how often people met in a social network. And this is really just a very faint relationship. You connected, you just signed off this LinkedIn request because you were like, oh yeah, sure, why not? And this is someone on LinkedIn or a favorite social network you're interacting with on a daily basis. Obviously, this edge attributes, this edge weight, should make this connection more important than the other. A very, very good point. Let's talk about graph neural networks. So graph neural networks, they in the end, they're also used for creating some kind of representation. The cool thing is we can treat them both in a supervised or unsupervised setting. So in an unsupervised setting, it would just generate our embeddings as such. But we can also have that in a more supervised setting where if we, for example, want to use the embeddings for node classifications. And so we can kind of use our graph neural network to create embeddings which are good for node classification or link prediction, trying to predict missing links within our graph. So how you can view graph neural networks, it basically creates a latent representation of our graph. And that might have then certain connections which are not there. So it's a transformed representation of our graph, potentially also with different weights, with different properties we just try to predict. One example of that would be Uber Eats. They have I find quite interesting blog post how they take this recommendation example we saw earlier with movies to the next level. So they pretty much want to predict, like they want to give you examples of what you might want to order, or from which restaurant you might want to order. So the graph for Uber Eats, it's not just a bipartite graph of users and dishes or products we saw earlier with movies. It actually is a tripartite graph where we have users, restaurants, and then dishes. And this is what they want to predict, like, hey, which restaurant might you might want to order from, or which dish you might even want to order. And so they train graph neural network for that, and this is the graph stage model we'll see on just in the upcoming slide. What are graph convolutional networks referring to? So you might be familiar with image or convolutional networks in general. So they are often used in image classification, for example, and here a convolution refers to we are moving a filter, or also called kernel, across the image, and we are trying to compute this one image. So this is one pixel value. So here we would take all those pixel values and, for example, average that, moves the filter to the next, moves the filter one further, calculates that vector, that value here, and so on and so on. So we're trying to convolve multiple items, multiple pieces of information into one. If you just try to view it from a very high level, what we're trying to say is that there are certain invariants which hold true throughout the entire space. So in the image, for example, we might have such kernel function or such filter function which detects pixels moving from dark to light, or which tries to predict a circle or something else. And so this invariant, this kind of function, black and white, holds across the entire picture. So we can apply that filter kernel across the entire image, convolve it across the entire image. If we want to do the same in general graphs, it becomes a bit harder because graphs don't have this regular structure. So a pixel doesn't have a right pixel, pixel doesn't have like a pixel below it or above it. We don't even have the same number of neighbors within our graph. So it becomes a bit harder, but for example, one notion which you might want to say, like all the neighboring pixels, all the neighboring nodes of a certain node might be in that filter out here. Of course, this is a variable size, and we'll see the challenges with that also coming up. But it's the same as if we would interpret it here, because also here it's basically all the neighboring pixels taken into account. Just in the image case, it's a much simpler definition because we have more structured, whereas in general graphs, we have to deal with a bit more unstructuredness out there. What can those graph neural networks be used for? Can, for example, be used for natural language processing. Again, recommender systems, as also the case with Uber Eats, or also scene graph decomposition when we want to do image analysis. The first ones were proposed, not the exact first one, but one of the first ones is this graph convolutional network based on message passing. So interestingly, if you recall what we talked about in with Pregel and those updates, where we are basically sending updates to all our neighbors, this is a pretty similar idea as we're dealing here with the early graph convolutional networks. So each of those nodes can send an update to its neighbors, and that can already include some notion of a feature. So this might be a particular feature, and there we are coming to Josh and Stefan's point is that we now can take like some more context into account, and then we are updating like our latent representation here, h1 new, based on some aggregate function. So it could just be a sum or something else, but basically we want to aggregate all the messages we have received. This is in the end also pretty simple to build. I will give a quick walkthrough. Let's see, as we have 16 minutes left, so I'll just give a brief overview of that. So I think it depends on like what is most useful for you. So for me, it's very helpful to see what's happening on a mathematical level below. So we can actually build such graph convolutional network from scratch just with matrix multiplication. So for example, here, we now really come to the representations we talked about in the beginning. We can represent a graph by this adjacency matrix here. And network X luckily also has a function to draw it from a NumPy array. So this is pretty much the graph represented by this adjacency matrix here. Now, how can we be just going to add like some random features? So it's we are cheating. Let's print that for once. It's right. Run that again. So we simply give each of the nodes. So node 0 is going to get 0, 0. Node 1 is going to get the feature vector 1, minus 1. 2 is going to get 2, minus 2. So it's a just very simple way of assigning like a random feature vector there. Now, as if we jump back to the slide of message passing, one step in such graph convolutional network basically means I want to pass my vector of information to all my neighbors. If we now look at the incidence matrix, and multiply it with our features, this actually means by terms of matrix multiplications that we distribute and sum over all our neighbors. So basically we take this inner part and sum over all the messages we are receiving. So let's do that. So for example, node 0 has received 1 and -1 as update. Let's look at that. It received 1 update from node 1, and node 1's feature vector is 1 -1. Great. Node 1 ends up at 5 -5. Let's see how that gets along. So here we receive updates from node 3 and node 2. And if we kind of add those two vectors up, we receive 5 -5. So we can actually implement this message passing by leveraging matrix multiplication using the adjacency matrix. Then just to keep that all in sync, we do some more steps. So for example, we add self loops because right now we would forget our own information. But if we extend our matrix, let's also print a hat. Just for brevity. Print a hat. So we can extend our matrix here by adding a 1 on the diagonal, meaning we also are adjacent to ourselves and we want to send ourselves the update. And then we can do things to normalize it. And then we can actually do things to learn and add also the nonlinear activation function. So we can really build such a graph convolutional network from scratch ourselves. In reality, we would never do that, but we would leverage libraries such as a deep graph library out there, which is implementing that for us. So if we take a look here at the next notebook, DGL, we have it much simpler to instantiate that and run it on the Karate Club network. Interestingly, now they expect directional edge, so they again expect another encoding. So they basically hear this an encoding like 1 to 0 with the source and destination. So basically have that adjacency list spread out across two different arrays. But in the end, we can just always move back and forth in between. Okay. This again is our already familiar network X graph. We can create our embeddings. So we want 34 nodes, dimension equal to 5. And then we can go through, label our 2 nodes, and then train it out here. Does that run already? That was fast. And we can now actually visualize those embeddings. So here, draw 5, this means after which iteration do we want to show it? Let's go to iteration 10 and see how that hopefully is pulling apart. Here we can already separate it. Let's go to 20. So iteration step 20 of learning. 30. It's not really changing too much right now. It's yeah, but here we can see with 5, they're already much closer to each other. And how many did we choose in total? Yeah, we see it's kind of like pulling more and more apart. And here, 33, this is the one node of the administrator, and this is the other one, and we see them getting much further apart. And so in reality, we would use a tool such as DGL for training our graph neural networks. And there are other, it's a quite powerful library out there. Okay, in terms of spending the last 10 minutes, let's give you a brief overview what we are missing and what modern techniques are being used for. So here's GraphSage. This is what the model or graph neural network which was used by Uber Eats as well, and it has certain properties. So already the title of the paper, Inductive Representation Learning on Large Graphs, it points out to two problems, the inductive representation and then large graphs. Let's start with the first one. So one of the major problems with early GNNs, and we already picked them out earlier, is it only worked with fixed graphs. So as soon as we change the graph, we would have to update it. So how can we learn on like an unknown graph or a changing structure? Take again LinkedIn or someone where we get more and more nodes added over time. So secondly, a second challenge is that those things, they require the entire graph during training, which severely limits the scalability to large graphs out there. And it's not like mini batches in normal neural networks where we can, on distributed nodes, train in mini batches and then upgrade an aggregate model. And those are the two problems GraphSage addressed. So first of all, they worked and made it into an inductive problem. So we can deal with changing or unknown graphs even. And how do they do that? So they basically just sample or create an embedding based on a sample of the neighborhood. So if this here is our target node, we want to aggregate over the aggregates of our samples. So this is kind of like a limited set. And so if we want to predict a new node, we need to sample this neighborhood and then apply our learned aggregation function. So kind of the model which is learned by GraphSage is this aggregation function here. And this can then be applied to unknown or changing scenarios without having to touch the entire graph. So it works on a pretty local part of the graph. Second part is they also worked on those kind of equivalent of mini batches in graph neural networks, which helps us to really scale it out to large scenarios by sampling always a fixed size neighborhood. So we can create fixed size samples. Again, keep in mind, those graphs have the disadvantage that we don't know how many neighbors a certain node has. And for creating mini batches, we would need have like fixed size mini batches. And so they created a sampling algorithm to deal with that. So they call it like neighborhood sampling combined with mini batch training. There's also a notebook for that. So this is an external one. So this is one I didn't write myself. I only moved it here because I had to do some changes to actually make it runnable. But there's a right attribution in there. The next problem we talked about was we have now the inductiveness, and we can take care of node features, because the messages also in GraphSage here, we can aggregate over some node features out here. What is then still missing is the edge features or the edge importance. And this is where graph attention networks are coming in, where we can basically learn which of the neighboring edges are more important or less important. And this might obviously, a simple determinant for that might be the edge weight we have here. So how important is this edge in between H1 and H2 here? And so I think with those different tools, there's also a lab for that. But with those, we basically have that evolution of graph representation learning. The most simple method we saw is just having random walks across a graph, generate those sentences, apply the node to vec, and we have our embeddings. The bit more smart thing to do was to actually have a guided random walk, so not just create random sentences, but based on those different parameters we have here. And those parameters allow us to take explicitly homophily or other properties of real-world graphs into account. Next, graph convolutional networks, they allow us to take into account node features. Next, GraphSage is taking that next step, allowing us to do inductive and distributed training. And then graph attention networks give us the ability to reason over edges and edge weights as well. So not treat each neighbor the same, but basically treat each neighbor depending on additional information with different priority, if you want to say like that. With that, we actually are at the end, or at the a point for questions. I wanted to reserve the last 5 minutes for questions, but before that, let me give you a brief overview where to go from here. So I understand this was a lot of information. We basically covered that entire space of graph learning, graph analytics. So there's a lot more in the slide deck. Also, feel free to reach out via Twitter, LinkedIn, etc., to me at any point in time. Otherwise, there's a number of books. So if you're interested in graph databases, there's Graph Databases in Action. Then there is the Practitioner's Guide to Graph Data. I think what they solve well, this is in particular the first part of that book, is the graph modeling. So how can you take a problem and turn it into a graph, or view it as a graph problem? Then the different graph algorithms we talked about, there's a book about them, graph algorithms. Then there is the graph-powered machine learning book. It's in combination of the graph analytics topics we talked about, and then the graph machine learning topics. And then this is, by the way, a free ebook as well, the graph representation learning, which covers the representational techniques, so the different embedding techniques we discussed in the last part of this. Furthermore, there's a Stanford course on machine learning with graphs, including the videos. Thomas Kiff, who wrote one of those first papers, has a really good blog post. And then there are a number of other links out here which might help you to dive deeper into that topic. With that, thank you so much for listening. Happy to answer now in 3 minutes some more questions. I'll also take some more feedback. Are you saying like this was entirely too much? Or is there some topics where you would like to know more about? As I said, also happy to add slides later on, as this is a live slide deck, which might keep evolving if you have particular questions. People are typing. Thanks, James. Also, as said, if you have any feedback afterwards, always feel free to reach out, or if you're also feel free to share that slide deck with your colleagues. This is open source. Also contribute, fix some typos in the exercises. This was sometimes it's this late night work when you or wake up early and you have this idea, I would love to add this one more exercise, then just sometimes typos sneak in. Apologies for that. Okay. Otherwise, if there are no further questions, connected data moderators, do you have any follow-up or can we otherwise close the session? Then I would just hit stop here. As I said, feel free to follow up. There's the other talk tomorrow where we compare a bit more the graph analytics techniques with a trade-off towards graph machine learning. Kind of spoiler is, we saw some of the questions earlier, it comes down to complexity versus performance in the end, but feel free to tune in there as well. Thanks so much.